Hey everyone. Today we're talking about horizontal resisted motion and then vertical resisted motion. So we'll first start off with the, I guess, easier one. And I say easier in that there's just like one less thing you have to consider. But horizontal resisted motion means that you're some particle, you're some object, and you're on the just one axis, and your position's given by x, and of course by time, and of course position is the same as displacement. So you might have 0, and maybe you're accelerating in some direction. Maybe you started off with an initial velocity, but then you might be, incurring friction or something like this. You might be subject to friction, or you might be subject to something that's helping you accelerate. Okay, so I guess there's not really much to it. It's always good to just keep in mind that we're going to the right is positive, going to the left is negative, but that just works like a normal x-axis anyway. So there's that. Okay, what I sort of recommend with questions, both in horizontal resisted motion and vertical resisted motion, is remembering, or not remembering, but always trying to look back to your second derivative. Oftentimes, these questions are given in your second derivative, i.e. as an acceleration equation. Right, there's always some x double dot equals. Okay, if the x double dot is made up of t's, the integration to find velocity and integration to find displacement is going to be different. If the x double dot is made up of x's, then of course that's going to take a very different integral as well. And if the x double dot is written in terms of v's, you obviously have a different form to be integrating that one as well. So you just have to keep in mind how these ones work, okay? And keep in mind all the different options you have for replacing x double dot with. So that you can replace x double dot with rather, and then try to look back and see which one's going to be relevant. I'll be pointing back and forth and trying to explain why which one's relevant in the question we're going to be using it. So hopefully that can help you as well. So remember, this is the same as d dx. Oops, we'll start with the easy one. D squared x on dt squared. It can also be written as d dx. Oops, no. Trying to write them all out in the order in which they come. But I think the next one's dv dt. The next one's v times dv dx. And the last one is d dx of a half v squared. Okay, so one of these is probably going to be relevant. Just decide which one and I guess take it from there to answering the question. So let's see what this first question says. A rowing 8 crosses the finish line with speed 5.5 meters per second and stops rowing. In a greatly simplified mathematical model, the boat is slowed by 2 drag forces. The skin drag is due to the surface area in contact with the water and is equal to a tenth of mv squared. And the form drag is due to the shape of the boat pushing the water aside and is equal to 100 mv. Thus, the force equation is given by mx double dot, so mass times acceleration, kind of like net force in physics, is equal to this thing here. Okay, so the idea is that I guess a good diagram is going to help us explain what's going on. We have like the x-axis or the displacement axis, and the boat starts off here. We can say, position 0 at t equals 0, and it's got a velocity of 5.5 meters per second. But what's happening is you have these forces pushing it back, because obviously drag, just like friction, always opposes the direction of motion. Okay, so this is a tenth of mv squared. But then you also have another one which is equal to 100 mv, and because we define this way as positive, those have to be negative. Wonderful. It says find v as a function of x. So mx double dot equals minus mv plus 10v squared over 100. Of course, I can cancel off these m's. Now I have to choose which form of dv of acceleration I have to use in order to be able to integrate. Okay, the first thing is, can I just say, oh yeah, velocity is going to equal the integral of this, and effectively just replace that with dv dt? No, I can't. The reason why is because I can't integrate this side with respect to t. You may then suggest, well, what if you took the reciprocal of both sides? What if you had it as dt on dv equals 100 on v plus 10v squared? You can now integrate this with respect to dv. Yeah, sure. In fact, you can. And you can even bother doing this if you'd like. My only concern with this is that the equation I'm going to get is is an equation with t's and v's. Whereas part A says you want an equation of v as a function of x. So yes, this is possible, but it's not necessary for this part. Okay, sorry. We'll say no to this. The next one that we have is v times dv on dx. And this equals minus, well, this should be a negative, like that. Negative v times plus 10v squared over 100. Okay. I think this is fine, actually. Okay. The reason is because if I divide by v, and I put a 1 on v there, I can cancel off the one of the v's in each of them, dv dx. It's going to equal negative, and then it's going to be 1 plus 10v over 100. And now I can't integrate both sides with respect to x, but I can integrate both sides with respect to v if I took the reciprocal. So the reciprocal would be dx on dv equals 100 on 1 plus 10v. We add a new page. I feel like this question's already quite long. And then now I can integrate both sides with respect to v. My left-hand side, these cancel, and you get the integral of dx, which is just x. And on this side, if I take, sort of pretend I sack that off and I just put a 10 there, then I put a negative 10 there. Obviously, that's the same thing, isn't it? But now I have derivative over original, which means I now have minus 10 ln of the absolute of 1 plus 10v plus c. Okay, and it's saying find v as a function of x. So I need v equals something in x, but I have some initial information. At x equals 0, v equals 5.5. So let's find out what this is. 0 equals minus 10 ln of 5.5 times 10 is 55. 55 plus 1 is 56. So 56 plus c. C equals 10 ln 56. And therefore, x equals minus 10 ln of 1 plus 10v plus 10 ln 56. How can we do this? Take out a negative 10, and you get ln of 1 plus 10v minus ln of 56. This equals, because we need v as the subject. So this is going to be 1 plus 10v on 56. And then if we take this back into index form, actually, no, I'm going to get rid of that and put it over 10 like this. It'll be e to the power of minus x on 10 equals 1 plus 10v times 56 over 56. Okay, rearranging this, I think you can see sort of what's going to happen. We're going to get v equals 56 e to the minus x on 10 minus 1, and then a tenth of the whole thing. Okay, nice. And then part B says, how far, select the nearest meter, does the boat eventually travel as it comes to a stop? So see how it says eventually? That's kind of saying as t approaches infinity. Okay. As t approaches infinity, we can just take the limit for part B. Oh, we don't have any t's, do we? Okay. So what I'm thinking we do is we go back and we find the dv dt form that we were talking about beforehand. Okay. Oh, damn, I feel like people, I don't know if you can hear the people in the back. But, okay. Well, anyway, Actually, no, we don't have to. Let's think about part B differently. As t approaches infinity, what should velocity approach? Velocity should approach 0 because you're decelerating because of the forces opposing your motion. So if that's the case, let's go to another form. Let's not go to this final form because it's written as v as a function of x. Let's go back to something like let's say this thing here. Okay, let's copy that because it's already got x as the function. So as v approaches 0, what does this thing approach? It just approaches ln of 1, which is equal to 0. So you end up with just x equals 10 ln 56. Okay, and 10 ln 56, where's my calculator? Equals 40 approximately. Okay, but you have to keep in mind, you have to give some form of reasoning for why as t approaches infinity, velocity approaches 0. This might not always be the case, depending on, I guess, the context. Alrighty. Oh, and by the way, I would not use that last form, d dx of a half v squared, because the only way I can do this, I can't even remember the question was, but was it 100 over, no, where was it? V plus 10v squared on 100. V plus 10v squared on 100. You can only use this if you're integrating with respect to x, and I can't integrate this side with respect to x at all. So I would not be using that one. Okay, how about the next one? An object of mass m moves horizontally, starting at the origin with velocity v0, where v0 is greater than 0. It experiences a resistance due to friction, which is proportional to the square of its speed and in the opposite direction. Obviously in the opposite direction, that's how friction works. Find the expression for the velocity in terms of displacement x. Okay, so this is where we have to be very general. And we're going to say, well, the friction is proportional, that's our proportional symbol, to the square of the speed. Okay? Now, but because, so how can we write friction now as a force? Well, if something's proportional, we can write friction as equal to kv squared, where k is the constant of proportionality. So that's the case. We can now write the net forces acting on this thing, on this object, is equal to minus kv squared because it's in the negative direction, isn't it? Right? And I guess you can see that because if this is your object, it's moving with the v naught this way, but this is friction. Perfect. So now, x double dot equals minus k on m, which are just constants, v squared. It's saying find an expression for v in terms of displacement x. So I'm obviously just going to be looking at the v dv dx. Why? Because this is the only one that works, right? Like you don't want to be using dv dt. There's no t's in here, so you can't integrate with respect to time. And nor do you want to. Even if you take the reciprocal and integrate with respect to v, it's asking for v's and x's. And the other one is d dx of a half v squared. But that one, you're forced to integrate with respect to x. There's no x on the right-hand side at all. So this is your only option. So dividing both sides by v, times v like this. Now, because I want to integrate with respect to v, I'm going to take the reciprocal of both sides. And I'm going to get dx on dv equals negative m on k times 1 on v. Now, if I take the integral of both sides with respect to v, I can integrate it like this, but obviously these are just constants, that minus m on k, so I'm just going to put it there instead. Left-hand side's x, right-hand side is minus m on k, ln of the absolute of v plus c. Very nice, very nice. Okay. Now, it seems like the velocity is always going to be greater than 0 because you're always moving to the right. So I guess we don't need the absolutes. Okay, I guess you can convince yourselves of that. If the only force restricting you is friction, you're never going to have a negative velocity. Like friction's never going to make you accelerate in the opposite direction with the new velocity that way, for example, or that way in the negative for you guys. Okay, so we know that. Find expression for v in terms of displacement x. So now we got to find the c. We go back to this. It says starting at the origin with velocity v0. So at t equals 0, x equals 0, and v equals v0. So let's sub that in. 0 equals minus m on k ln of v0 plus c. That means c equals m on k ln of v0. Good. If we go back to this, we get x equals minus m on k ln of v plus m on k ln of, and then just be careful because you're gonna have a bunch of v's and v naughts and stuff. So capital V naught. Summoning everything by minus k on m, you're gonna get minus kx on m equals ln v minus ln vo. Okay, and then this is minus k. And then by rearranging this, we get v on v naught equals e to the power of minus kx on m, and v equals v naught e to the power of minus kx on m, like that. Sick. And it says, damn, some people are very loud. I don't know if you can hear them or not. For a certain 5 kilogram object, the resistance is equal to 1 on 10 v squared. Find how far the object has traveled when it is slowed to a quarter of its initial speed. So let's just copy this part down. So that m equals 5. If we look at the form for friction, it was in the form kv squared. So it means this here, k equals 1 on 10. Find how far the object has traveled when it has slowed to a quarter of its initial speed. So we find x when v equals a quarter of v naught. Not slowed by a quarter, slowed to a quarter. And the initial speed, of course, is v. Wonderful. So let's go to this. A quarter vo equals e to the power of minus k, we know what k is, minus 1 on 10 x over m, which is 5. Like this. Obviously, that's a quarter vo equals, vo there, which of course these cancel. Quarter equals e to the power of minus x on 50. Taking ln of both sides, we get minus x on 50 equals ln of a quarter. And then that means x equals negative 50 ln of a quarter, which using index laws is 50 ln 4. Okay, and I guess you can sub that in if you want, but this is going to be in, I guess if this was all in meters and stuff, I can't really remember. I don't know, whatever, units. Nice. Okay, I guess have a go at this. You'd be given the velocity and you need to find the displacement as a function of time. So x in terms of t. Alrighty, unpause once you're ready. Let me show you. This one's quite easy. It's dx dt equals VO e to the minus kx on m. Okay. Oh, I think this is relating to the part before. So maybe you can use the whole at t equals 0, x equals 0, and v equals 0, or v equals v0. So that's fine. So we'll say this is continued. Obviously, we can't integrate both sides with respect to t because we have x's on the right-hand side. So I'm going to take the reciprocal. Taking the reciprocal, quite easy. So it's going to be 1 over VO, but instead of it being e to the power of a negative, it's going to just be e to the power of the positive version of this. Integrating with respect to x, integrating with respect to x. Let's chuck this integral actually there. We're going to get t equals 1 over VO divided by the derivative of the power, that's k on m. So divided by k on m is multiplying by m on k, e to the power of kx on m plus c. Now, following from that part before, we were told at t equals 0, x equals 0. So 0 equals m VO k. That's whole e to the power of 0 is just this 1. So this is plus c. Damn, these are very, very annoying questions to do. And therefore, t equals m on VOK e to kx on m minus m on v0 k. And then we need it as x as the function. Find displacement as a function of time. So let's multiply everything by v0 k on m. I know this is poor notation, but it is what it is. V0, yep, that's supposed to be a k. I thought that wasn't clear. So v0 k t on m equals e to the power of kx on m minus 1. Adding 1 to both sides, taking ln of both sides. So we're going to get kx on m equals ln of v0 kt plus m plus 1, and then x equals m on k. There you go. So, bro, sucky question, but it is what it is. Alrighty. I want you to have a go at this question. Yeah, this is not related to earlier parts. This is just on its own. Okay, once you've had a go or an attempt, I shall now go through this. So it says mv dot is equal to minus kv squared. It says find the time taken for the speed to reduce from v0 to a half of v0. So it seems like we need an equation for t's and v's, because v dot is acceleration, isn't it? So m, instead of writing that as v dot, I'm gonna write it as dv dt equals minus k v squared. Nice. I think I'm gonna take the reciprocal of both sides. Maybe actually I'll divide by m first. And then you get dv dt equals minus k on m v squared. And then if we take the reciprocal, we get minus m on k v to the minus 2. And then integrating both sides with respect to v, just like that, put it there. We get t equals minus m on k. Adding 1 to the power dividing by the new power makes that a positive, makes that a v to the minus 1 plus c. Now, here's actually a good point. You can do this in 2 ways. You can do it by, because you can't really evaluate c, right? There's no constant that we haven't been given some extra initial conditions. So you can write it in terms of c, because you're saying find the time taken for the speed to move from v0 to a half of v0. You can sub in v as v0 and sub in v as a half of v0, find the times, and then take the difference. But what you'll recognize is that that c cancels off anyway. So an easy way to do this is to just take the integral as a definite. So take it as a definite integral from a half of v0 to v0. Okay. Actually, no, it says from v0 to a half of v0. So from v0 to this. Okay. It's actually pretty sick. So let's see. I want you to do it both ways, and I think you'll recognize that it works. So t equals minus m on k, and then it's negative 1 over, and it's a half of v naught, so this becomes 2 on v naught, and then minus plus 1 on v naught. You will get the same thing, even if you use c's and sub in the two values for v and take the difference between them. Trust the process. One on v naught, so this just becomes mkv0. Nice. That's really horizontal resisted motion. I don't think it's that hard, to be honest. I just think that you have to keep in mind which form of the acceleration you're going to be using. Okay. Sometimes it'll give you different equations. Some of them are more useful than others. Sometimes you might need to do both, you know. So that's that.
Alrighty, and now we're back to vertical resisted motion. So as opposed to horizontal motion, whether it's resisted or not, there's always this one thing that's lingering in the back of these vertical resisted motion questions. And that's the fact that there's gravity, okay? Now, gravity always pulls downwards, but the issue is on the way up and on the way down, there's another force which is acting in different directions, okay? So what forces act on any projectile as they move up or down or as they move through the air, okay? So unlike in physics, we pretend there's no air resistance, but here there is air resistance, okay? And that's something that's important. So what we're gonna say is imagine that you have like the ground. And I mean, we're doing a lot of Y's for vertical. So I guess instead of using x dot, x double dot, we'll use y dot, y double dot, but it doesn't actually matter, right? It's still displacement, velocity, acceleration. So we'll have this y equals 0 at ground. Now, if you have a ball, why is that not turning into a ball? There we go. And it's thrown upwards. What's happening is it's going to go up, it's going to reach some peak, and it's going to go back down. Now let's consider what the two forces are. So the forces we have first, we have weight force, which is given by mg. Now, weight force is always acting downwards. Okay, always. Makes sense. Gravity never pulls you up off the ground. And then the other one is drag / air resistance. Okay, and this can be given by whatever formula they decide to give you. Sometimes it's MKV, sometimes it's MKVN, whatever. Okay, whatever it is, let's just call it FD, so drag force. Now, it doesn't always act down and it doesn't always act up. The way drag works is the force always opposes the direction of motion. Okay, and this is all about law of conservation of energy, things that people would learn in physics. For example, if the ball's throwing up, drag should be pulling you back down because you're moving up. If you were throwing a ball up and drag was also up, it means it would accelerate the ball upwards, but that's not how balls work in the real world anyway. So if we consider on the way up, F net, which equals mx double dot, or rather my double dot in these cases, is going to equal, well, what forces are acting downwards? We have drag force and we have weight force. So we're going to have minus mg minus fd. And of course, that's because moving upwards is positive. Okay. But on the way down, we have F net, which equals my double dot, so mass times acceleration, is going to equal, well, negative mg, because that's always going down. But now the ball's here. And as it moves downwards, drag force is upwards. So it's going to be plus FD, whatever that FD formula is. Okay, so this is important. So when you do a question like this, and we always start with acceleration, the acceleration equation, so that differential, it's important to note that if there's a question and it's throwing a ball up and then back down, you can never model that using the same differential. You have to do one separate model with one separate set of formulas for on the way up, and then one separate model with another set of separate formulas for on the way down. Okay, this is very important. Anyway, the rest of those rules apply, like the v, dv, dx, and all of that business, except now instead of x's, it's all y's, whatever. So let's consider this example here. A particle is projected upwards in a medium for which the resistance to the motion is 1/5 of the mass times the velocity and opposite in direction. Okay. So the initial velocity is 30 meters per second. Let y be its height in meters above the point of projection after t seconds. Use g as approximately 10 meters per second squared. Okay, so a good diagram, I think, is going to help us. This is the ball, and it's projected upwards. Well, at t equals 0, what do we know about the y value? It's 0 because it's projected from like the base, right? Well, everything is relative to where it's been projected from, so we can consider that to be the ground. And the y dot, which is the velocity, is positive 30, okay, because it's thrown upwards. Nice. So they gave us that y double dot equation, but I think we could have figured that out ourselves. Remember, this is mass times double dot. That's an F net is equal to minus mg, and then minus, and then look at how they describe the resistance. The resistance to the motion is 1/5 of the mass times the velocity. And it's in the opposite direction. So 1/5 of mass times the velocity, v. Okay. Now, if you divide everything by m, because the m is common, and you take out and you sub in 10 rather as your g, you get y double dot equals minus 10 minus 1/5 of v, which is equal to minus and then 10 plus 1/5 of v. So we could have gotten to that ourselves. It says find y as a function of the velocity and hence its maximum height. Okay, so what are our formulas for this? Remember, all of those rules we had for acceleration are the exact same, except now instead of x's, they're y's. So the old ones were d dx over half v squared equals, well, I'm starting on the wrong ones. D squared y on dt squared equals dv dt, which equals v times dv, and then we'll write this as dy because it was dx, so now it's dy. And then this is also the same as saying d, and it used to be d dx over half v squared, now it's d dy over half v squared. There's no harm in just using x's anyway, and just having all of this in terms of x, as long as it doesn't say it's not a show question. Okay, but whatever. Actually, no, this one says find y as a function of the velocity, so I guess you need to use y's. All right, whatever. Now, which of these ones will we be using? Okay, I'll copy them down so that you can see them down with the rest of the question. Copy. We have a formula. We're trying to find y and v. So we have a few options. We have this one, and we have this one. I'm thinking if I use this one, I can only integrate with respect to y. But integrating this side with respect to y doesn't make any sense because it's got v's in it. So instead, I feel like this one's the way to go. Yes, I hope you all agree. So now we have v times dv on dy equals minus, and then I'm just gonna make this a common denominator. I feel like that's probably gonna be useful. Actually, yeah, let's make a common denominator. So that's gonna be 50 plus V all over 5. Now, dividing by V, we get a V there, and that goes away. Okay. Now, again, I still can't integrate with respect to Y, so I have to take the reciprocal. So it's 5V, negative 5V on 50 plus V. Okay. And now we just have to integrate this with respect to V. So what I'm thinking is we have to sort of maybe take the negative 5 out. So here we get Y, and we take negative 5 out, and we get V plus, and then you guys should be pretty good at this by now. I'm thinking add 50, subtract 50, because then you get Y equals negative 5, and then it's integral of, actually we don't even need this, 50 plus V on V, 50 plus V on 50 plus V is just 1. And the other one's minus 50 on 50 plus V dV. Of course, we can figure this out. Just like that. This is going to be V minus 50 ln of the absolute of 50 plus V, and then plus C. So Y equals minus 5V plus 250 ln of 50 plus V plus C. Nice, 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 nice. Now we need to find C. Do you see how it says here, at Y equals 0, Y dot, which is also another way of saying V, equals 30? So I think we can sub that all in now. So at Y equals 0, V equals 30. Is it 30? Did I read that wrong? No, 30. Perfect. So 30 equals minus 5. No. 0 equals minus 5 times 30 plus 250 ln of 80 plus C. So it seems like C equals 150 minus 250 ln 80. Okay. 150 minus 250 ln 80. Now, where are we going to go from this? Let's consider. Okay. Oh, damn, we have so much more to go. What does it say? Find Y as a function of V. Oh no, we almost did the Y as a function of V. Y equals minus 5V plus 250 ln of 50 plus V, and then plus 150 minus 250 ln 80. Okay, nice. Now, that's that. It says, hence find its maximum height. So you physics students will already know this, but as a bit of a reminder, I have my AirPods here, okay? And when you throw something up in the air, at the very peak, the velocity is 0 because it's in between moving up and moving down. So its velocity is 0. And you can sort of see it at the very top kind of stop before it goes back down, even for an instant, you know? Maybe that's a bit of a refresher on year 11 physics. So, and projectile motion from physics as well in year 12. So what we can say is at max height, V equals 0 because it's the highest point before it starts turning back down. So now we can just sub in 0. Minus 5 times 0 plus 250 ln of 50 plus 150 minus 250 ln 80. Cleaning this up, we get 150 plus 250, and I'm going to take a bracket out and say ln of 50 minus ln of 80. This is 150 plus 250 ln of 518. Okay. And then this is some number. So I guess if I chuck this in, 150 plus 250 ln of 518. So like 32.5 meters. There you go. Nice. So that's an example of an upwards journey. I feel like hopefully that makes sense. Okay. What's this example? A particle falls from rest. So now it's falling from rest. Through a medium for which the resistance is proportional to the velocity and opposite in direction. Let y be in the distance in meters below its initial position after t seconds. Okay. So it says, assume y double dot equals g minus kv. So this is where you got to be a bit careful. I would love to define downwards as negative, always, consistently. But for some reason, in these show questions, because they're separate parts, they define downwards as positive. And you can see that, right? Because even in here, this is positive g. So it means it's accelerating down with positive weight force. And then the drag, which is pushing it back up, is got a negative next to it. So as long as you're careful, if it was fully up to you, do whatever you want. All the questions are going to work out as per usual. But here, they've given it to you like this. So just maybe do a little bit of a diagram for yourself to sort of see what's happening and just put an arrow and say downwards as positive so that you don't make the mistakes that I guess we would probably assume would happen from like in physics and stuff. So here we are, we're being thrown downwards and this is positive. There's the ball there and it says, what does it say? Okay, they've given us this. I guess it doesn't tell us anything about its initial position. Oh no, I guess we do know at t equals 0, y equals 0, but we don't know the velocity. Or from rest actually, so we know v equals 0 as well. Nice. So just, I say as I ironically didn't do, but read the question carefully and make sure you've sort of picked out everything in it, just like in physics. So we have y double dot equals g minus kv. Actually have a go at finding v as a function of t. Try and do this question all on your own. Okay, I want to see what you guys end up getting to. Anyway, assuming that you've just had a go because you've paused my video, let's replace y with, I'm thinking v dv, no, sorry, dv dt, because I want v as a function of t equals g minus kv. Now, of course, I'll take the reciprocal, dt on dv equals 1 on g minus kv. And then integrating both sides with respect to dv, or with respect to v, I need a negative k there. And so I'm going to put a negative 1 on k there. And that's going to be a ln. So then this is going to equal t minus 1 on k, ln of the absolute of g minus kv plus c. Now, what do we know? At t equals 0, it was dropped from rest, so v equals 0. So I mean 0 equals minus 1 on k, ln of g plus c, and that means c equals 1 on k, ln g. So now putting this back together, what did it say? Find v as a function of t, so v equals something. So we have a bit more work to do. Minus 1 on k, ln of g minus kv, plus 1 on k, ln of g. I'm thinking multiply everything by negative k. We get negative kt equals ln of g minus kv minus ln g. Putting this all together, yeah. I feel like I'm rushing it, but hopefully I'm not making any mistakes here. E to the negative kt equals g minus kv on g. Multiplying both sides by g. We get g, e to the minus. Bro, I'm saying too many letters. This is not good. Okay, and just follow this working. And then there you go. Oh, thank God. Alrighty. What does the next part say? Hence show that the terminal velocity is limit as t approaches infinity, v equals g on k. So why do we actually have terminal velocity, right? Like why is that a thing? First of all, terminal velocity is defined as the maximum speed or the maximum velocity a falling object can possibly reach, okay? And you might say, but if they're always accelerating downwards, then why is it that you're ever going to have a maximum velocity? Shouldn't you just keep increasing in velocity? And the answer is like sort of yes. If you always have acceleration, then you're always going to have velocity, like a change in velocity, and you should always be speeding up downwards. But you get to a certain point where the weight force, okay, well, basically you can not push the air particles out any further, any quicker rather, okay? So you've gotten to this point where you're going so fast that you can't possibly, depending on your surface area or whatever, you can't possibly move those air particles out to displace them once your object takes that place, okay? And it's at that point where the net force equals 0, okay? Because you can't push them any more than weight force is pulling you down. And the net forces, they all equal to 0, and therefore you are no longer accelerating. Now, why do you still have such a high velocity? It's because before you were accelerating, so you still sped up a lot, but there's a certain point where you can no longer go any faster, okay? And you can see there's actually 2 ways for us to get to this. I'll show you both, okay? Now, what can we tell? Terminal velocity is as t approaches infinity. So this is part B. So what happens to our velocity equation as I take the limit as t approaches infinity? First of all, this is a negative exponential, so that's going to approach 0, isn't it? As the powers get a greater negative number. So velocity approaches g on k. Okay, so that's one way of doing it. I mean, it says hence, so in that case, this is the only way of doing it because you have to use part A. But to show my point about net force equaling 0, go back to your y double dot equation, which was g minus k minus kv. We have terminal velocity when y double dot equals 0. So just setting this to equal 0, we get kv equals g, which means v equals g on k. And that's the same thing. So it works both ways. Unfortunately, we can't always use the second method because sometimes our second derivative is not written in terms of velocity. It might be written in terms of some other rubbish. Okay. So we've done this, we've done this. It says find y as a function of t. Actually, not that bad. If we look at this velocity equation here, let me copy it, paste it down so you can all see. If we look at this one here, just recognizing that v equals dy on dt means we can find an equation for displacement and time. So dy on dt equals g on k 1 minus e to the minus kt. I don't know why I wrote that all in red. Let's change this to blue. And then, of course, integrating both sides with respect to t. So we get y equals g on k. Then we get t plus 1 on k e to the negative kt. You can check my work if you'd like, but that's facts. Now we got to find, I shouldn't use c or use d because we used c before. D is a constant. What were we told? At t equals 0, y equals 0 because it was dropped from a particular position and we're defining that position as the origin. So let's sub this all in. 0 equals g on k, 0 plus 1 on k, e to the power of 0 plus d. And I think we get d equals negative g over k squared. Yeah, that should be right. So then therefore, y equals g on k, t plus 1 on k, e to the minus kt, minus g on k squared. Okay, you can leave it like this. You can expand it if you like. Could not care less. Alrighty, next part. Show that if h is large enough, then the approximate time to reach the ground at y equals h is given by this. Okay, so I think we got to take the limit as h goes to infinity. So let's just copy this down so that we can see what the question's even asking. Okay, so if h is large enough, as soon as you see something like this, consider limits, right? So we want to take our y equation as g on k, t plus 1 on k, e to the minus kt, minus g on k squared. Like clearly we're using this somehow. Dare I say, what am I daring to say? This thing going to 0. So when would h be super large? Like when would, if h was super large, doesn't that mean that the time has to be super large because it means it has to fall a greater height? Making that connection is going to save us a lot of time. Okay, so of course, if the height you are falling is longer, then the time it takes for you to get to that position is obviously going to be longer. So let's sub in, or let's take instead, I was going to say h goes to infinity, but we don't really have any h's in here. So what we should say is, as t approaches infinity, let y equal h. So h equals g on k. But what I'm going to do is I'm not going to change this t. I'm going to leave that t. But what I'm going to say is, well, this t here makes this exponential go to 0 a lot quicker. So that's why, because this goes to 0 a lot quicker than this one does, I can replace this with 0 before I can replace this with 0. So that's okay. So t plus 1 on k times 0 minus g on k squared. Okay, I think we see where this is going. H plus g on k squared equals g on k t. And then multiplying both sides by k on g, we get t approximately, because we still we took these limits, is going to equal kh on g plus 1 on k. That should be right. Let's go. Okay. Done. I think I just have one more question here. And then we're finished. So an object is thrown downward with initial speed twice its terminal velocity. I guess you can maybe find its terminal velocity already. Its motion is affected by gravity and air resistance. Initial speed, that's not only that, twice its terminal velocity. Its motion is affected by gravity and air resistance, which is proportional to the square of its speed. Put the origin at the point of projection downwards as positive. Fair enough. The velocity v satisfies this equation with the initial condition that v of 0 equals 2vt, where v of t or vt equals the square root of g on k. Bruh, if this was me in an exam, I would not have given that square root of g on k. I would have hoped that you all listened to my point about y double dot equaling 0 when you have terminal velocity and being able to rearrange this to get v as positive the square root of g on k. Okay, but that's just me. I think you can have a go of this on your own. Okay. Wait, what is the question even asking? Bro, did I not copy in the question? Am I a bit inept? Did not put the questions in. Okay, well, let me just paste this in. I feel like such a boomer. So close to the camera over there. Please. Let's go. Okay. let A equal, oh, A says let omega or W equal V on that thingy. Bro. Okay, so I guess it's asking let this new W variable be the proportion of the terminal velocity that the velocity is. Okay. So let's figure this out. It seems like we took V dot, which is equal to G minus KV squared. And we may have divided everything by VT. Because V dot should equal, sorry, W dot, we're going to assume just is V dot over V0 or VT, my bad. Okay. So it seems if I divide everything by that, that should work. Or maybe if I'm being a bit smarter, actually, let's say that means V dot equals W dot times VT. And that means V equals W times VT. And I think we should replace everything that we have there with this. So now we have part A. Bro, this is such a sack question. This is going to equal W dot VT, which equals G minus K times WVT all squared, which actually, sack, let's just write this as squared and squared. Now I'm thinking, if I divide every term by G, oh no, by K, on K, on K, on K. Actually, no. Let's see what we can do with this G and this K, because we don't have any, oh no, we do have the square root of GK. Let's divide by VT, 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 and VT. We're going to get W dot equals G on VT minus K on VT. Oh, that's all one term, times omega squared VT. Okay. Let's just consider, I mean, VT equals the square root of G on K. So what does G equal? So G on VT, let's see, VT squared equals G over K. Okay, I think I have it. All I gotta do is replace this G with KVT squared. I think this is gonna do us wonders here. W dot equals KVT squared over VT minus KW squared VT. See, this cancels off with that. And let's take out what we have as a HCF. Well, it seems like we have as HCF K and a VT, and we have 1 minus W squared. Oh my God, thank God, bro. And then KVT. No way. Oh, that was wild. Okay, so what does that equal? If I times this by K, and that becomes K squared, then I can square root both sides and get KVT equals square root of GK. Okay, this was a very interesting question. GK 1 minus W squared. Nice, whatever, we got that done. Oh, we didn't, we just need to take a negative out. There we go. Okay. It says show that W satisfies this and state the initial condition for W. So what's going to be the initial condition for W? Well, it seems like W equals V over VT. but at t equals 0, so we can say w0, w of 0, is going to equal 2 vt on vt, which means that's just 2. Nice. Okay, part B. Use partial fractions to help find t as a function of w. Okay, so t as a function of w. So t equals, and then w is on the right-hand side. So let's come to this. We were given w dot is equal to minus the square root of gk, w squared minus 1. W dot is the same as dw over dt. dw, like Arthur, you know, that show. Okay. Now I can't integrate both sides with respect to t, or yeah, I can't integrate both sides with respect to t, because obviously there's w's on the right hand side, so I'm gonna take the reciprocal. So dt on dw equals minus 1 over square root of gk, and then times 1 over w squared minus 1. Of course, integrating both sides with respect to w, put that there. This is t equals minus 1 over the square root of gk times. Now we have to do partial fractions on this. So, so Siebes. Obviously, this is w plus 1, w minus 1. So let's just do this. Multiplying by the denominator, like this denominator, we get a w plus 1 plus b w minus 1 equals 1. Let w equal 1, we get a equals a half. Let w equal minus 1, we get b equals minus a half. Perfect. So that means I can take out a half from this entire thing. So we get a half, and the integral of a, the positive, was on w minus 1, and then the negative was on w plus 1, dw. T equals minus 1 over the square root of gk, 2 square root of gk, and then times, now this is going to be ln of w minus 1 minus ln of w plus 1. Yep. And then plus c. Okay, so minus 1 over 2 square root of gk, ln of w minus 1 over w plus 1 plus c. Okay. Now we were given at t equals 0, where is this? T equals 0, w0 equals 2. So let's chuck that in. W minus 1, so 2 minus 1 is 1, over 2 plus 1 is 3, plus c. By making this 3 to the minus 1 and taking that negative down, that cancels off with this. So c equals negative 1 over 2 square root of gk ln 3. And then what we can say is now, therefore, t equals minus 2 over, well, this thingy, times ln of w minus 1 over w plus 1 minus 2 gk ln 3. What I'm thinking is, this is 1 over 2 root gk ln of w plus 1 on 3 w minus 1. Okay. I did that by just factoring this out, taking the negative, putting it in there, these swap positions, and then dividing by minus ln 3 means, I'm sorry, minusing ln 3 means dividing by 3 within the ln. Nice. Okay, so I think that's that. And then hence find the time taken for the object to reduce in speed from 2 vt to 11 on 10 VT. So this 11 on 10 VT is not the W, that's just velocity. But remember, W equals, we'll write it in a different color, your velocity over that. So it's like 11 on 10 VT over VT, which is 11 on 10. So let's just sub that in. (11 on 10 plus 1 is 21 on 10 over 3 times 11 on 10 minus 10 is 1 on 10. Just by simplifying this, we get 7. There you go. We should be good. Alrighty. That's how you do all of these questions. So I hope it didn't seem like I was bombarding, but that's how you do all these resisted motions. Choose which differential you want for the derivative for acceleration, and then just work at it from there. Just be careful with your integration, especially when you have so many unknowns, like the G's and the K's and all of that. So just be careful, okay? Maybe sometimes M as well. Other than that, that should be it for me.